This looks almost like a comet. In fact, if I hadn't read the legend, I would have thought it's the caption. I would have thought it's a comet, but it's an asteroid. It's spewing out gas. It's outgassing, as they say. That's pretty cool. So it's got a tail. Let's see, what is this? This is. Anybody figure out what this is a picture of here? Let's see.
If I had Venus. That's on Earth.
No, the object in the foreground. Let me turn the light off so you can see it better. The object in the foreground is not Earth or Venus or Mars. Those are Earth, Venus, and Mars are tiny little dots in the picture.
What is that?
It's Saturn.
The one with the ring.
Yeah, it's the one with the it's Saturn. It's an eclipse.
You can move the line of like Earth and Moon, and like anywhere on there it would make a difference. If you just took the Earth and Moon and the line that's supposed to be labeling it and moved it.
Yeah, nobody would be able to tell. I know you can't really see very well. So that's looking back at the sun, but with Saturn in the way, right? So it's an eclipse. It's a solar eclipse from behind, taken from behind Saturn in the Saturn shadow. So you can see the sun is behind Saturn, and I don't know what this kind of glowing stuff is. I don't know what that. Unless that's maybe that's thinner rings or something.
What, inner rings?
But you can see the light passing through the atmosphere of Saturn. It's pretty cool. And you can see the Earth and Moon and Venus are, of course, all closer to the Sun, and so they're going to be.
Is this an actual photograph?
Yes, this is an actual photograph from.
Wait, hold
from
on. It almost looks like it's been like painted all. So how does that?
Cassini. This is a picture from Cassini. Cassini went through Saturn's shadow, and they turned the spacecraft back around to look at in the direction of the Sun, except of course it's blocked by Saturn. So it's pretty cool. Okay, let's see. Welcome back to 309, Cooper. We've been gone for a little while. Office hours this Friday will be only the after class from 2:30 until after class. I'm not going to. I have a doctor's appointment in the morning, so I can't make the earlier 2 hours. If anybody was planning to come to my office hours on this Friday, during those times, let me know and we'll schedule some other time. If you can't come in the afternoon. Okay, so now let's go over the worksheet for the rigid body. So this is an exercise really in calculating moments of inertia for bodies of different sizes, different shapes, different configurations. So, and it points out that in general you can count on 3 principal axes. That is, what's a principal axis? Somebody help me to remind us of that, Mr. Avery. Mr. Kelly.
It's basically like a core axis of rotation that the body would be able to be rotated around. Like there's an X, Y, and Z.
Yeah.
Now that we spun.
And what's special about it? Mr. Covington.
Isn't it the axis where the angular momentum and the angular velocity are going to be pointing in the same direction?
Exactly right. And because for a rotating body, if there's no torque, the angular momentum will be a constant. Therefore, the axis of rotation is also a constant, so it spins nice. But if the angular momentum is not parallel to the axis of rotation, which is the general case, that they're not parallel. And again, if the angular momentum is a constant, then for the thing to keep the angular momentum pointed in the same direction, the axis of rotation has to change while it rotates, which means it's going to wobble. It gives that funny wobbly motion. It's rather complicated. And you'll study these equations. They're really very difficult to solve exactly, but you can solve them in certain special cases when you do the junior mechanics. for now, we're going to assume that we are spinning around a principal axis. So a principal axis usually is easy to spot if the body has a lot of symmetry. If it has a lot of symmetry, it's a symmetry axis. Usually the symmetry axis is a principal axis. And so if you spin it around a symmetry axis, usually you will see that that is a principal axis and it spins nicely around a symmetry axis. So it's not exactly the same, but for the purposes of this, we'll just assume that the principal axis is a symmetry axis. Okay, so I give the example in the text. The text considers a cylinder, for example. Well, obviously an axis that passes along the axis of the cylinder itself is a principal axis. And then any axis that passes through the equator would be a symmetry axis as well. So there are lots of principal axes. And the moment of inertia is different for these different axes. So depending on how it's spinning, then you'll use a different moment of inertia. Okay, so for the solid cylinder of length L, radius R, then if we're spinning it around the central axis through the center of mass, then the appropriate moment of inertia from the table is going to be 1/2 mr squared. Notice that L does not come in to the moment of inertia if it's spinning around that axis, because L does not determine. What's important in the rotation is how far is each little piece of the body from the axis of rotation, and L does not come into that when it's rotating that way. So, for example, the angular momentum, if it's spinning around that axis with angular velocity omega, the angular momentum will be 1/2 mr squared omega. And the kinetic energy will be 1/2 I omega squared. So it'll be 1/4 mr squared omega squared. Note all these factors of 1/2 floating around that have to do with things other than the 1/2 of the kinetic 1/2 that comes into the kinetic energy, for example. Okay. Whereas if we wanted to spin the cylinder around this other axis, around this that passes through the equator, what would you call that? Central diameter, right? So a central diameter, if the axis of rotation is a central diameter, then the moment of inertia, the appropriate moment of inertia for that is, God bless, 1/4 mr squared plus 1/12 ml squared. And clearly here, both R and L come into the determination of the moment of inertia. So you have to know specifically what L and R are in order to know specifically what the moment of inertia is. But again, the angular momentum is going to be that moment of inertia times the angular velocity, and the kinetic energy will be that moment of inertia times 1/2 and omega squared. Okay.
Excellent question.
Yes, sir.
If we threw in a third axis, would that just be the same as the central diameter?
If you pick an axis which is perpendicular to these other two,
so one coming out
that would also be another central diameter, right?
So it would be the same zone.
Yeah, there are any axis that passes through the equator would be a central diameter.
So you can say there's like infinitely many.
Yes. In this case, there is any axis that passes through the plane of that central diameter is its principal axis. You can always pick 3 that are mutually perpendicular. So if you want to, then the third one would be coming through the central diameter again, also in the plane of the equator and perpendicular to the other 2 that I drew on here. So those would be 3 that are perpendicular, mutually perpendicular.
So all 3 are. So the principal axes, are they always mutually perpendicular?
Yes, sir, they are. That's an interesting thing. They're always mutually perpendicular. Yep. And the proof of that is interesting, and you'll get it in your junior year if you can wait. If you can't wait, I'll give you a book and you can figure it out from there. It's an interesting fact. Okay. So now we're going to consider rotation of a sphere, and the sphere has is given mass and given radius. But I'm going to use two different spheres. One of them is a solid sphere, and the other is a hollow sphere. Same mass in the two different cases. So looking up in the table then for the solid sphere, you find that the associated moment of inertia is 2/5 mr squared, and the moment, I'm sorry, that's I, and the moment of inertia for the hollow sphere is 2/3 mr squared. So which has a higher moment of inertia and why? Why should it be that way? The lecture camera seems not to be capturing anything. Let's see here. There it is. Ah, okay. Hold on. Sorry, I'm sorry to be distracted here.
You good?
Okay, and I need to turn on the light over here. So, Mr. Jackson, why is it that so which one is the solid sphere has a lower moment of inertia than the hollow sphere? Why does the hollow sphere have a higher moment of inertia
It
than
has to
the
do with
solid?
the fact that its mass is concentrated farther away from the center of mass?
Yes, exactly right. Specifically, if you look at each piece of the sphere when it's spinning, each piece of that sphere is executing uniform circular motion around the axis. And the bigger the radius of that circle that it's moving along, the higher the associated kinetic energy and angular momentum. The kinetic energy goes like the square of that distance. So that's why the moment of inertia has a mass times the length squared. It's the mass times the contribution of that piece is the mass times the square of the radius of that little piece, the circle that little piece is orbiting around. Add them all together, and you get the total moment of inertia for the sphere. So this is a nice problem for doing integrals. If we were doing integrals, we would calculate the moment of inertia using integrals. You'll do that when you're in junior mechanics. You'll calculate the moments of inertia using integral calculus. Three-dimensional volume integral. Nice problem. It's a nice exercise in volume integrals. But the reason for it is just as Mr. Jackson said, that the farther out the mass, the higher the associated kinetic energy or angular momentum. So if I take a disk, a circular disk, where the mass is spread uniformly around the disk, or if I take a wheel, where all the mass is around the rim, it's the same mass and the same radius. Which one is going to have a higher moment of inertia? Yes, or the bicycle, the one with all the mass distributed around the rim, because there's more mass farther away from the axis of rotation, and that gives it a higher kinetic energy, higher angular momentum for the same mass, same total radius. Okay. So now suppose we're spinning it around something that's not a center of mass, which I could easily imagine doing. For example, taking a pencil and letting it fall over. The rotation occurs around the end of the pencil, not around the center of mass. A door is rotating around on the hinge, not around the center of mass, but around one edge. If I have an incline and I have a ball that's rolling down the incline, it's rotating instantaneously around its point of contact with the surface. So in that case, you would want to be able to calculate the moment of inertia in that case, which is going to be different. The table mostly has entries for rotation around the center of mass, and the two examples we just did here involve that. So if it's rotating around an axis parallel to a principal axis but shifted away from the principal axis, then you can use the parallel axis theorem. So let's take, for example, let's suppose that we have a sphere, and we just said that the moment of inertia of a solid sphere, doesn't have to be a solid sphere, but the moment of inertia for a solid sphere, what did we say? It was 2/5 mr squared. And let's suppose we were going to rotate this thing somehow around an axis that touches the surface of the sphere. So maybe we could tape the sphere to the axis and spin it around the axis then, something like that. Hook it to the axis somehow. So it's definitely spinning not around the center of mass, and this whole thing is going to rotate around the axis, right? So if we wait later, the whole sphere will be down here as it rotates around this axis with frequency omega. So the moment of inertia, the question is that axis parallel to a principal axis? Well, every axis is a principal axis for the sphere. Every axis is the same. Any axis is a principal axis. And so this is indeed parallel to a principal axis. So in this case, then, the moment of inertia is obtained by taking the moment of inertia about the center of mass and adding a term ml squared, where L is the distance, perpendicular distance between the two axes of rotation, which in this case is equal to the radius of the sphere. Right. So therefore, the moment of inertia is 7/5 mr squared for that particular type of rotation. And again, it's quite high. It's much higher than the moment of inertia for the sphere around the center of mass, because more of the mass of the sphere is distributed away from the axis. In fact, very little is along the axis, just grazing the surface of the sphere. So there's a big moment of inertia for this thing to spin around that kind of axis. So this makes it very convenient. Okay, yes. So let's consider a wheel rolling on a table. Now this problem might involves a little bit of something that you don't know about yet. We hadn't really talked about. So I'm curious to see how people did. So let's suppose we have a wheel rolling on a table. And the rolling is without slip. So there's no slipping on the table. So when you consider something like an object moving on a table, it could be spinning, but the fact that it's rolling without slipping is very special. If you've done any bowling, you know that a bowling ball can be sliding and spinning, but not spinning without slipping. It's slipping as it rolls, right? When you start it off, as it gets farther down the lane, sometimes it will get in sync and start rolling without slipping. But you can definitely get it started where it's sliding, spinning a little bit, but not spinning fast enough to make it roll without slipping. What we're talking about here is that it's rolling without slipping. So that puts a special constraint on what's going on here. So let's consider there's two things going on. There's a rotation, which is measured by an angle, theta. How far is it rotated? And it's translating, which is represented by a distance x along the horizontal. And this thing has a radius r. Now, if this thing is rolling without slipping, there's a relationship between the speed of translation and the speed of spinning. So let's think about it this way. Let's suppose we had started that the ball was here, and it rolls without slipping a distance x. And in that process, it rotates an angle theta. What is the relationship between x and theta? Mr. Jackson?
Between x and theta?
Yes, sir.
Well, they're analogous, but won't be r theta?
Yes, sir. Exactly right. And why is that?
Because the r is the distance theta it's traveled.
In a sense. You could suppose there's paint on the table and you want to see how much paint ends up on the balls. In other words, you're mapping this distance onto the ball, right? And so that arc length is going to be the same as that distance. And that arc length is in fact r theta, where theta is the amount of rotation. So x equals r theta. This is called the no-slip condition. This guarantees that the ball is rolling without any slip. It rotates exactly the right amount that is just rolling on top of the surface without any slip. Now we could also take the derivative of this. If x equals r theta, then we could take the derivative. If the radius is constant, then we have the velocity is r omega. In other words, the translational velocity is related to the rate of rotation, the angular velocity of the rotation. And if it's accelerating, or even if it's not accelerating, we take another derivative, and any acceleration in the x direction is going to be accompanied by angular acceleration. The body's got to spin up faster. If it's going to be accelerating, it's going to spin faster as well. So these are all expressions of the no-slip condition. You're going to see the no-slip condition cropping up in these problems all over the place because it's a lot easier than dealing with something that's slipping. It introduces rotation in a little bit different way than we've seen before. Okay, so now let's suppose we have this wheel is rolling without slipping. Now there's two ways of dealing with this. What we want to know is what is the kinetic energy of this motion? There are two ways of accounting for the kinetic energy. Way one is to consider the body, to consider the motion to be rotation about the point of contact. If it's not sliding, then you can consider that instantaneously, right at the point of contact, it's rotating around that point, just at this instant. So what is the kinetic energy of that? Well, all we have to know is the associated moment of inertia for rotation around that axis, which we just did. So you use the parallel axis theorem. So the moment of inertia that we're going to use is the moment of inertia about the center of mass plus mr squared. This is the parallel axis theorem. And so the kinetic energy then is 1/2 times the moment of inertia at the center of mass, around the center of mass, whatever that is, times mr squared times omega squared, where omega now, remember because of the no-slip condition, is related to v through the no-slip condition. So we could write that as 1/2 I center of mass over r squared plus m v squared. Pretty that up a little bit. So it's 1/2 mv squared. So the 1/2 mv squared is the kinetic energy of translation, and the 1/2 cm omega squared. So this is the kinetic energy of translation, and this is the kinetic energy of rotation around the center of mass. So that's the second way you could do this and get the same result. Way two is the kinetic energy of rotation around the center of mass plus the kinetic energy of translation of the center of mass. So that would be then 1/2 I cm omega squared plus 1/2 mv squared. And we just have to remember again that v is related to omega. They're proportional to each other. So we can write it in terms of one or the other. Okay, so you see the point of the two different ways. They get the same result. You can pick either way of doing it. The first way is to consider that instantaneously it's rotating around that point of contact and use the parallel axis theorem. The other way is to say, well, it's got two kinds of motion. It's moving like a body was before, which is just translation. So we have the kinetic energy associated with that translation. And now it's also spinning. So we have the kinetic energy of the rotation. And they happen to be related to each other because of the no-slip condition. The translational velocity and the angular velocity are connected to each other because of no slip. Either way, you can do it either way. Okay. All right. So, any questions about that?
Actually, I'll wait till afterwards. It's not too important.
It's not important?
It was just a conceptual, perhaps thing.
Okay. All right. Well, I'll rely on your judgment. We'll talk about it after class. Okay, so let's take the following example then. You're going to do this for homework. Oops. All right, you remember this problem we did before? We had two masses connected by a rope. The rope goes over a pulley. So we have M1, M2, and in the previous problem we calculated the acceleration of the masses. There's gravity associated with this, and you could do it with or without friction. We could throw friction in, get kinetic friction on the table. Okay, and then we calculate the acceleration with or without kinetic friction. You should know how to do that. All right, here's the new wrinkle. Anybody see it?
Factor the turn of the pulley.
Right, yeah, we neglected the mass of the pulley. We said it was a massless pulley. We neglected the kinetic energy or the torque on the pulley. We just assumed that it was very almost massless pulley. In fact, we considered it to be massless, negligible mass. So now we're going to put mass on the pulley. We're going to consider that the pulley has some mass and some radius associated with it. So it's got some mass and it has some radius. And now we're going to work out the problem again. See what's new here. So just like in the previous problem with the massless pulley, you should be able to do this problem one of two ways. Either with Newton's equation or with the work energy theorem. If you want to find just the velocity of the mass at the bottom, then the work energy theorem is enough. If you actually want to find the accelerations and the tensions in the rope and the time it takes and the more details, you work it out through Newton's laws. So let's work this out through Newton's law. You're actually going to do this through the work energy theorem when you do your homework. But I want you to see this problem done like we did it before, but now with the rotation present. Okay. So what do I need? What's the first step?
Force diagram.
How many bodies are there?
3.
So I need 3 force diagrams. And let's suppose for simplicity there's no friction. We can go back in and put friction in later. So how many forces are acting on this body, the one that's on the table?
3.
And the body that's hanging, how many forces are acting on it?
2.
The tension and the weight. Notice that I did not assume that the tensions are the same. In the previous problem, when we did the massless pulley, we asserted that the ideal rope and pulley would preserve the tension all the way through the rope. But in this case, it's not going to be true. The tension is not going to be the same all the way through the rope if we have the no-slip condition on the rope. The rope is turning that pulley without slipping. So we still have a condition here is more realistic, and that is that the rope will turn the pulley. It will apply a torque to the pulley. To torque it, start it accelerating. So let's look at the force diagram for that pulley. It has mass M, radius R. How many forces are acting on this?
The 2 torques.
Yeah. Is there another one?
Gravity and gravity.
Yeah, there's gravity.
Mobile force.
There's some force that's holding it into the assembly, right? There's something holding onto the axis that keeps the thing from falling or doing anything else. So there's got to be some other force associated with the axle. The axle is exerting some force on this thing as well. There are 4 forces on this thing. Now it sounds hopeless at first. You think, oh my goodness, how am I going to find all of these forces?
So where's the force, that other extra nuclear force that you put?
Fa is the force because of the axle. The axle is exerting force on the wheel to keep it in place.
And where's that in relation to the wheel?
It acts on the center. It acts on the axle, right? Right through the center of the wheel.
So we don't have to consider the pulley on that, though, do we?
Ah, of course you do.
So wait.
Okay, it looks common.
Gravity on the pulley.
Because
Sure, there's gravity on the pulley.
No, but like
You don't have to factor it into if you're like trying to find distances and stuff that stuff's moving.
Somehow it doesn't come in, does it? But let's see how
because
this
of the
works.
axle.
Yeah, but how's this going to work?
But what about friction
All right.
with the axle on the
All right, the next step, you'll see where it's going. The next step here will be to write Newton's laws, Newton's equations of motion, and, first we need a coordinate system. Okay, so going back to the diagram, I'm going to define this distance as x1, this distance as y2, and then I've got an angle, theta, associated with the rotation of the pulley. And 3 coordinates. And there's going to be, in principle, 3 accelerations, but one of them is an angular acceleration. But they're all going to be related to each other. Okay, so let's begin by writing Newton's equations. Let me do this in this color. Okay, so looking at this, right, that's easy. The only force on that body is the tension in the rope. And the other body, M2, Y2 double dot, is the weight minus the tension in the rope at that point, the other part of the rope, the second part of the rope. Now what's the third equation of motion? It's going to be the angular acceleration involving the torque. So it's going to look like this, or I guess I could use theta double dot here. It's analogous to Newton's equation, right? Where we have mx double dot, we have I theta double dot. And we need the torque. Well, we got 4 forces acting on it, so if we compute the torque around the center of mass, is this rotating around the center of mass? Yeah, the axle is going right through the center of mass, makes it nice. So we have 4 forces acting on that, and when each one could possibly produce a torque, but 2 of them don't. 2 forces produce no torque around the center.
Gravity and that axle thing.
Yeah.
Wouldn't the axle be stopping it?
Right, because the moment arm, the distance of the force from the point of rotation is 0. So R cross F for those 2 forces is 0. Right? If we want to compute a torque, in general, it's R cross F, and if R is 0, that is if it's applied at the center, then there's no torque associated with that. How about the torque? So does everybody see that, why the torque due to gravity is 0?
Yes.
If I take a wheel and put an axle through it and hold it like this, and gravity is acting on it, and in fact the axle is also producing a force up this way, there's no torque on it. It's not going to accelerate the wheel. It's not going to make it spin faster, right?
Oh, because it's acting in like all directions, even the clockwise and counterclockwise way.
You can
positive and negative
see it in
both directions.
by symmetry. You can see that it's not producing a force.
It's all uniform, you can just put it in the center.
Right. Okay, so there are only two torques around the center of mass. So the torque around the center of mass is going to be the radius, the distance, which is r, and then I get the difference between the tensions. That's the torque. Can you see why those 2 forces produce torque in opposite directions?
Yes.
One is trying to spin it forward in one direction, the other one's trying to spin it backwards. And if those 2 tensions were equal to each other, then there'd be no torque on the pulley, which would mean it would not accelerate, which means that nothing would be accelerating in this system. Okay, so let's look at this.
Could it be sliding over it?
But we said it's not. We said it's no slip.
Okay.
Yeah.
But if there was 0 torque, could it, like...
Yeah, well, certainly it could be slipping, right?
Yeah.
And that's going to be a more complicated situation. So we take baby steps,
So
tiny
what
steps
axis?
for tiny feet, right? I haven't told you the story, so probably. Right, Richard Feynman's advisor at Princeton was John Wheeler, and John Wheeler worked with Einstein, right? So Feynman goes into Wheeler one day and tells him, and he says, "I've been working on this. I don't understand this." He shows Wheeler and he's explaining this, and Wheeler goes, "Tiny steps for tiny feet." Right.
Ooh, wait, he was that dirty?
Yeah.
Bro, I'm
Yeah.
sorry for what I
So,
said. I need him to
tiny
do
steps
this.
for tiny feet. No little. Let's do the no slip condition first. Come back later, do friction and slipping and all that stuff. All right, let's slow it down. Okay, so we're going to do. We've got the no slip condition, but this is where we start off here. We start off with 3 equations, but we haven't gotten everything in here yet. There's more that we haven't put in. Remember when we did this problem before, we said that the rope was a fixed length, and that puts a constraint that relates the accelerations. The 2 accelerations are the same. Do you remember that? X1 double dot and Y2 double dot are the same because of the fixed length of the rope. So ideal stretchless rope. Let's just call that A. Now what's the other condition that we have?
That A is, that the rotation is not slipping, so the rotation has to be equal to the distance to go. So A is equal to R, that alpha kind of thing.
Right.
Theta double dot, theta triple dot, it's all the same.
So this is the no slip condition. Okay, so now we can go back and look at our equations here. There's the first one. M2A is equal to M2G minus T2. And the third one then is I alpha is equal to RT2 minus RT1. But that alpha is going to be A over R, so I'm going to rewrite this as, stop. Here we go. Write alpha as A over R. Okay, we have 3 equations now. How many unknowns? What are the unknowns here?
The accelerations.
Acceleration?
The T1.
R is known as part of the geometry thing. So
The 2 tensions.
the 2 tensions, right? We said they weren't the same. Actually, we're going to find out what they are, and we should see that they aren't the same. There's no way that they can be the same. Okay, so this is an algebraic problem. You just solve for 3 unknowns, 3 linear equations, and do your thing. Might simplify it if we made the 2 masses the same. That would make it a little simpler. Okay, I haven't worked it out. Yes, sir. We could work it out real quick here. Why not? Let's do. Let's make them. I'm going to try here without making mistakes. Y'all will catch me, so I have confidence that I can do this.
Wait, the masses are the same?
Because I know that. Yeah, I'm going to make the masses the same just to make it simpler.
What?
Yeah,
It's
yeah.
cheating.
Right. Let's see. And then, so I want to put the. There we go. So what if we add all 3 equations together? The tensions will cancel out. So one way to do this is to add all 3 together. So if we do that, then I over R squared plus 2m times the acceleration is going to be mg. And so the acceleration is going to be the mass of the hanging weight. The ratio, that ratio there.
Where'd you get over R squared?
Yeah, I divided the third equation by R, so I could get just the tensions by themselves, because I saw by looking at it that if I get the tensions by themselves, then I can add the equations together, and the tensions will cancel out. So therefore, you find the acceleration. Let's suppose that the moment of inertia is 0. We want to recover our previous answer. If the 2 masses are the same, then this acceleration will be 1/2 of g, which is the answer we would have gotten if we'd done this problem previously with masses the same. Okay, so that gives you an idea for how to do this. I know I've gone here pretty quickly, but you should be able to go back and follow all these steps. It's basically the same thing that we've done before. What's new here, of course, two things. We have the equation of motion for the pulley, that is the rotation of the pulley, has been added in. And we have the non-slip condition that constrains the acceleration of the masses to the acceleration, the angular acceleration of the pulley. And then those two things now are new, and we put them in, and we can now solve just like we did before. It's basically the same thing that we've done before for the acceleration. So let's see here. Okay, let's do a dimensional analysis before we do that real quickly. What's the dimensional analysis of I?
M1 squared.
Yeah, any moment of inertia is a mass times the square of a length, right? So looking at that expression, we have I divided by the square of R. And so that's going to be a mass. It's going to have something of dimension mass in the denominator over here. You see I'm looking over here. That's got dimensions of mass, and it's added to something with mass, so that's good. They should have the same kind of dimensionality, or it wouldn't work. Okay, Mr. Kelly.
Back for the torque.
Yes.
When you did our process, so we're not actually like doing Cartesian components. We have to write out like, vectors and stuff. Like, is that just the magnitude?
Well, it's a very easy problem though. You see R cross T2. Let's look at the torque. So I'm going to draw this. Let's examine the torque on that pulley a little bit more carefully here. So we have a rope that's coming off tangent to the circle, right? That's T1. And then we have another rope that's coming off tangent to the circle. What does it mean, tangent? Well, it means that it's perpendicular to the radius at that point. And the magnitude of the cross product, remember, R is the magnitude of the two vectors times the sine of the angle between them. So what is the torque produced by T1? Well, it's RT1 in magnitude because those two are perpendicular to each other. This is a right angle right here. And what's the direction of the torque? The torque vector. Right, it's R cross T1 out of the board. Does everybody see that? The torque is out of the board, right? Means that force, the T1, the tension on the rope that way, wants to accelerate it this way, counterclockwise. Whereas the torque, so that would be out of the board. How about the torque due to T2? Well, those are also perpendicular. R cross T2 at that point of contact, that's also perpendicular. So the torque due to T2 has this magnitude, RT2, into the board. It wants to make the pulley spin up clockwise. It wants to increase the rotation this way. So they're in opposite directions. And you have to remember, when I defined the angle, I defined it in the clockwise sense. So the acceleration of that angle is going to be into the board, right? So in other words, tau 2, T2, the force on that rope is accelerating it in the clockwise direction, and so it should be the torque then it's associated with theta is going to be RT2 minus RT1, right? They're in opposite directions. So I did the cross product. I'm not writing down a detailed coordinate system and all that stuff. It's not really necessary because it's so simple, right? R cross T, R and T are perpendicular to each other, and so it's just the product of R with the magnitude of T, and then you just have to keep track of the two different directions involved in the torque. You want to see it in...
So we just don't have to put like Z hat?
Right, in this case you don't really need to. The main thing is to account for the motion that you see, right? When you set up the coordinate system here, the main thing to capture is what's moving. The sliding of the block along the table, the dropping of the other block down, and the rotation of the pulley. Those are the things you want to take into account.
So you should think about the primary definition first.
Yes.
If it's easier, and then if it's...
That's correct, yeah. It's generally, you start with the primary definition. If it's a simple case, if it's really simple and symmetric, then the primary definition is going to be quicker. If it's something a little bit more complicated, then very often the Cartesian form of the cross product is going to be easier to calculate things. But in really simple cases, the primary form is going to be much easier to deal with. Okay. So, any questions about that? Let's look briefly at another problem. Instead of having a block sliding down a ramp, we're now going to have a rolling object. It's going to roll down the ramp without slipping. Roll without slipping. And we want to know how fast it's going to be rolling and what kind of acceleration it will experience, because now it can roll, not just slide. Okay, so again, let's set up Newton's equations for this. Look at the force diagram first, set up Newton's equation.
Is it going to have friction?
Yeah. It's going to, yeah. Oh, you know what? We did forget this. I'm sorry. Okay, so let's look at this. What forces are present on this object? Let's do a force diagram. There's a normal force. Gravity is going to act on the center of mass. And now maybe you can start to understand why I've been wanting you to draw gravity acting on the center of mass, because it acts symmetrically on all parts of this body, so it acts easier to account for it as though it acted on the center of mass. There's no torque produced by gravity in this case. Doesn't try to spin the body. Not about the center of mass. Any other force is present. Rolling without slipping.
Static friction.
There's static friction, right? And what is the magnitude of static friction?
U sub S normal force? Right?
Max value.
No, that's the max value.
Wouldn't it be the max value if it's being overcome?
Is it being overcome? It's just rolling. It's not sliding. It's not on the verge of sliding.
Is it accelerating?
It's going to have to accelerate.
Alright, so if it's accelerating, then this is good. Alright, so
If you take a ball and put it at the top of an incline, will it accelerate when it rolls? Certainly. It's accelerating, right? Whether it's sliding or rolling, it's going to accelerate. Okay.
Mu sub S, mg sine the same, or mg cosine.
What's that?
It's saying mu sub S mg cosine, but that's just the same thing. That's just saying mu.
Yeah, that would be mu sub S times the
That's
normal
still
force.
just the max.
But that's the maximum value
Okay,
of the static friction. The static friction is whatever is required to keep it from sliding, and we don't know what it is yet. Makes it a bit of a challenge. In fact, it's going to be part of what you find out in this problem, is what is the force of static friction in this case.
is that for homework?
Yeah, it is in your homework. So I'm helping you out with your homework.
Alright guys, I guess we're going to be going to sleep.
So give me just one more minute. I'm going to set you up here. We've got the force diagram. We need coordinates. What two coordinates would describe this motion? Yes, and let's draw theta this way, because that's the way it's going to start rolling, right? It's going to roll that way, and then the other, let's draw x down this way. And there's a no-slip condition. X is going to be proportional to theta. That's the no-slip condition. Or the acceleration is proportional to the angular acceleration. Okay, now we have an equation of motion for each coordinate. What's the equation of motion for x? It's just going to be Newton's equation. Mx double dot is going to be mg sine theta. I'm sorry, we got to be careful here. We got too many angles floating around here. We've got two angles. One of them is the angle of the incline. Let's call it phi. And the other is the angle of rotation of the rolling body. We don't know what Fs is. Okay. And how about?
Moment of inertia.
Yes.
Theta double dot.
right? Now, are you thinking of this as rotating around the center of mass or around the point of contact? Either way is going to be okay, but it has a different moment of inertia. So I'm going to opt at this moment for the center of mass because in this case there's really only one force that produces a torque around the center of mass. Gravity doesn't. The normal force does not because the radius arm is perpendicular to the normal force, right? The cross product is 0. And so that only